At the atomic scale, heat and sound are carried by phonons, the quantized normal modes of classical lattice vibrations. Topological band theory was originally formulated for the electronic realm, using a framework that relied on fermionic properties like spin-orbit coupling and Fermi surfaces to define stable states. This creates a fundamental problem for lattice dynamics. Phonons are neutral bosons that lack spin, carry no charge, and do not follow the Pauli exclusion principle. Despite these differences, classical Newtonian vibrations can acquire geometric phases and host rigorous topological invariants. Mapping these vibrations to topological rules provides a new lens for investigating how heat dissipates in semiconductors and how sound moves through waveguides. Standard lattice dynamics are typically modeled using a second-order harmonic dynamical matrix to track atomic displacements. This second-order form cannot directly calculate the geometric Berry curvature needed to identify topological phases. To bridge this gap, the classical equations of motion are transformed into a first-order, Schrödinger-like eigenvalue problem. This mathematical transformation allows for a consistent analysis of both artificial 2D acoustic metamaterials and natural 3D crystalline solids. This process establishes an exact mapping of lattice dynamics into a Hermitian phase space. We start with the mass spring equation of motion, transforming the classical variables into a mass-weighted matrix, dk. Recasting this into a first-order block matrix, hk, lets us integrate velocity coupling terms. Inside, the eta k variable represents gyroscopic or Coriolis coupling. When eta k equals 0, Berry curvature is strictly odd in momentum, and the Chern number vanishes. Realizing a non-zero Chern number requires introducing a synthetic time reversal symmetry breaking field to ensure eta k is non-zero, achieved through active non-reciprocity, external Coriolis forces, or Raman spin lattice interactions. Ultimately, the precise value of the eta k matrix determines whether these complex bosonic systems can support robust one-way chiral topological phases. In a 2D phononic honeycomb lattice, preserving inversion and time reversal symmetry, gapless Dirac cones form at the K and K' valleys. Applying a gyroscopic bias breaks time reversal symmetry, opening a gap. This generates an integer Chern number and a chiral edge state. This creates a quantum anomalous Hall phase, enabling backscatter immune transport. But if we break inversion symmetry with an AB sublattice bias instead, the gap opens with Berry curvature mapping contrastingly to the K and K' valleys. In this case, the global Chern number vanishes, resulting in a quantum valley Hall phase. This phase produces valley-polarized interface states, appearing only at domain walls where the inversion-breaking mass flips. Whether the system exhibits chiral edge transport or valley-polarized states depends strictly on broken symmetries. Moving from 2D models to natural 3D crystalline solids increases the complexity, as we must account for the dense atomic unit cells of real materials. To calculate these dynamics from first principles, we use density functional theory, or DFT. Using DFT, we calculate the real space interatomic force constants of a crystalline unit cell, which define effective phonon hopping amplitudes. These constants are Fourier transformed into a momentum space dynamical matrix, generating a continuous map of phonon dispersions across the Brillouin zone. Solving this matrix yields the specific phonon eigenfrequencies and normalized eigenvectors for the material. These eigenvectors form a fiber bundle, allowing us to compute the Berry connection across momentum space. Integrating the Berry curvature then reveals the Chern numbers and the location of Weil monopole charges. This computational framework allows us to search massive crystal databases for topological band crossings before any physical samples are synthesized. One material identified by this workflow is the B20 type chiral crystal FESI. FESI lacks both inversion and mirror symmetries, a structural configuration that forces non-trivial degeneracies in the phonon bands. Calculations for FESI predicted a charge 2 Dirac phonon at the Brillouin zone corner and a spin 1 Weil phonon at the zone center. To observe these modes, researchers utilized high-resolution inelastic X-ray scattering, or IXS, to measure the dynamic structure factor. This chart compares the predicted phonon band dispersions of FESI with the actual data points measured in the lab using IXS. The linear crossings visible in the data confirm the presence of these topological phonon modes. This agreement shows that the mathematical framework for topological phonons accurately models the lattice dynamics of real materials. Beyond mimicking electronic states, phononic systems can host topological phenomena that are not accessible to fermions. In electronic systems, multifold while nodes with high Chern numbers, such as plus or minus 4, are only possible if specific spin-orbit coupling is present. Bosonic phonons can achieve these high Chern numbers through crystalline symmetry alone, as seen in the material BAPTGE. Calculations suggested BAPTGE would host a two-fold quadruple while phonon at its gamma point. This momentum-resolved spectrum of BAPTGE shows the spectral intersection at the gamma point, which represents the first observation of a two-fold quadruple while node. The data shows that these chiral phonon wave functions exhibit opposite chiralities at time reversal-related momenta. This topological framework provides a predictive link between the thermal transport of atomic crystals and the engineered properties of acoustic metamaterials.